Okay, so continuing with our discussion of redistribution, we looked at up to this point doing redistribution on a single point in the network, which is not going to cause any problems either with the metric or any type of route looping, because the router internally knows what routes originally came from OSPF or what routes originally came from EIGRP. Now, problems in redistribution designs typically happen when there are multiple points for the same protocol meeting and when there are multiple points of redistribution. And there's generally three reasons that these problems are going to happen. Okay, the result is that we end up in a routing loop where the routers keep advertising the wrong information back to each other, or the routing topology is stable but at the same time is incorrect, which would be considered a traffic loop or a traffic black hole. Basically means that one router points out the wrong interface and eventually the traffic is going to get dropped. But the reasons why this would happen foremost is that there's reconvergence going on in the topology after some sort of change. Now, this is a normal situation in the network. If one of the nodes goes down or a link goes down, it's going to take some finite time for the network to ultimately reconverge. So depending on how we've designed the network with things like fast layer 2 link detection or fast hellos, how the maybe the SPF pacing timers are working and stuff like OSPF, that's going to be a function of the convergence. So when the network is changing, there's going to be some sort of packet loss. And normally in a high availability design, it's our goal to try to minimize whatever that loss is, albeit normal. Now, the two that are problematic are going to be feedback in redistribution that is based on metric or feedback that is based on administrative distance. Okay, these two are not normal, and they happen because your design is wrong in the first place. So you're either redistributing on the wrong points, or you're using the wrong metric values for seeding, or you just need to simply change the physical topology in order to accommodate what your particular goal is. So here we have an example of a metric feedback loop where we have the RIP domain connecting between routers 1, 2, and 3, and it is going to do redistribution into OSPF. So first, router 1 sends some route to router 2. And in this case, we're learning it on router 2 with a metric of 5. So whether that's directly connected on 1 or it's some prefix that's coming in from behind router 1, router 2 says this is a RIP route. It's via router 1. The metric is 5. Okay, next step, router 2 redistributes it into OSPF. So routers 4, 5, and 3, they learn this as an OSPF external route. The administrative distance is going to be 110 by default. Metric type will be E2, and the metric will be 20 by default, assuming we're not modifying any other parameters. Now, when this gets back to router 3, if 3 redistributes the route back into RIP with a lower metric value, now router 2 is going to have incorrect information, and the route is going to loop around and around the network. So router 2 is basically saying, I have two paths now to get to this prefix. I have the one that's coming in from router 2 with a metric of 5, and I have the one that's coming in from router 3 with a metric of 1. So since they're the same longest match to the destination, we're choosing the lower metric value and installing that into the routing table. Now, when this occurs, it doesn't stop the redistribution into OSPF. So effectively, router 3's route that's going from OSPF into RIP gets fed back into OSPF again and around and around and around and around. So when we try to actually send traffic to the destination, we'll see that it's going to cause a traffic loop between these 4 neighbors. So in this case, this would be an example of feedback that's happening based on the metric value. Now, the second variation would be based on the administrative distance. So for some reason, the router is making the wrong decision, choosing the wrong protocol in order to get to the destination. Because remember, when we look at the equal longest match route in the same protocol, we compare the metric. If we have the equal longest match route between different protocols, then we look at the administrative distance. So same type of case here, router 1 is advertising a route into RIP. It comes in to router 2 sends it to 3. Now router 3 is going to perform redistribution of RIP into OSPF. The problem now is that router 2 has two paths to the destination through different protocols. We have the original RIP route with an administrative distance of 120, and the new OSPF route with an administrative distance of 110. So what now will happen is that router 2 is going to install the OSPF route, which also means it must withdraw the RIP route. Because if it's not in the routing table from RIP, then we can't advertise it through RIP. The router 2 is going to withdraw it. Okay, router 3 now says, I don't have a route to the destination through RIP, so I can no longer redistribute it into OSPF. So we send a withdraw message to 5, 5 withdraws it to 4, 4 withdraws it to 2. This is going to happen over and over and over. Now where 2 originally advertises the route to 3, it gets redistributed, it eventually gets withdrawn over and over and over. Now this type of change is a little bit easier to troubleshoot in the network because the result is that we would see the network is entering and leaving the routing table over and over and over. So the route's in what we call a flapping situation. So it's going up and down over and over and over. There's a couple different tools we have in iOS to check this. We can see this from the output of the debug IP routing, what information the router is actually installing or withdrawing from the routing table, and a feature that's known as the IP route profile that can give us some statistics on what's happening inside of the routing table. The first variation with metric, that's a little bit harder to track down because we wouldn't see an instability in the routing table. We would simply see that when we tried to get to the destination, you can't reach it. And if you did a trace route, then you would see that the traffic goes around in a loop between these 4 neighbors. So before we look at this on the command line, how to actually fix these problems, let's talk about what are the different tools that we have in iOS in order to deal with this. Now, some of the problems we can only fix them by simply changing the topology design or changing where the redistribution happens. In other cases, we may be able to fix them by using route map filters, distribute lists, prefix list, access list, passive interface, and route tags. And the last one is kind of an interesting tool that we can do a type of automatic filter in order to prevent these type of problems from happening. Now, the first one we took a look at a little bit yesterday in BGP and today in redistribution, which is the route map. Okay, the main job of the route map is going to be for 3 different applications. One of them is for redistribution. Second is for modifying BGP attributes. And the third is going to be for policy routing, which we'll talk about a little bit later this afternoon. Now, there are other minor applications, but those are going to be the 3 main ones that route maps are used for. So in our case, we're going to use it for filtering based on redistribution and possibly modifying different attributes of the route. Now, for routing purposes, most of the time the route map would match a prefix list, which we already saw in the command line, which basically says, I want this exact address with this exact subnet mask. But there are some other attributes that we can match. An access list could be standard or extended. The route type, so is it internal or external? The route source would be where we are learning it from. The route tag is the administrative tag. We'll get into that later. Then the actual metric value. In the metric value, we could match a range. We could say, look for metrics between 10,000 and 20,000. So once we match these different criterias, the main point of the route map is that we are going to be filtering routes as they go between the different redistribution points. So in the previous design, where router 3 was feeding the route back into RIP, if we had a route map configured that said simply don't allow that route to go from OSPF into RIP redistribution, then the loop would never occur in the first place, because router 2 is not going to receive the multiple routes back in. Okay, the next one we have is a distribute list, which is used to selectively permit or deny routes as they're being sent on an interface, received on an interface, sent to a neighbor, or received from a neighbor. Now, the problem with the distribute list is that it can only be applied to RIP, EIGRP, and BGP. We cannot use this in OSPF or IS to IS because it breaks the link state database logic. So remember, with how OSPF shortest path first calculation works, is that before we start the algorithm, everybody in the area needs to agree on the same database. So if we're doing some type of filtering with distribute lists, different routers can end up in different answers for the shortest path tree, and we can end up in a traffic loop or a routing loop. So IS to IS doesn't even support the feature. OSPF, you can do some minor filtering from the database to the routing table, but usually it's not recommended. Okay, there's no way to filter an actual LSA out of the area other than when you're doing inter-area designs. Now, we saw that already with things like stub areas, where that filters based on the LSA type, but we're not filtering inside the area, we're doing it between areas. Now, the distribute list itself is going to call either a prefix list or an access list to do the classification. So the distribute list is the actual application of the feature, but the route itself will be matched inside of either access list or prefix list. Now, prefix list would be the preferred method for doing any type of routing filter because the syntax is very straightforward with the logic. We're matching on both the prefix and the length at the same time. So if we have the exact route 1.2.3.0/24, we simply need this one line that says IP prefix list, whatever the name is, I'm calling it list. We're saying permit this exact address, that exact match, that exact mask. So in this manner, the syntax is pretty straightforward. Where it gets confusing is when we start to match ranges of prefixes or ranges of lengths. Now, one thing the prefix list cannot do that an access list can do is to match on random bit patterns in the field. So with an access list, you could classify all numbers that are odd or all numbers that are even. Okay, with a prefix list, you can't do this because you can't match on random bits. But what it would allow you to do is say, for example, permit any address with a subnet mask that is less than or equal to 32. We could also say, look for any network that starts with the number 10, but has a subnet mask somewhere between 24 and 28. So it's used to match on either an exact route or a range of addresses and a range of address masks or subnet masks. So this is how in BGP, for example, a service provider could limit the routes based on the subnet mask that is received from the customer. So let's say, for example, that, and let me open up a whiteboard here. Let's say, for example, that we have router 1, who is the provider edge router, and it has a BGP peering with router 2, who is the customer edge. Okay, so the customer is advertising routes upstream to the provider. Provider says, I have an aggregation policy defined that I will only accept routes that have subnet masks of 0 to 24. So if we have /25 to 32, we want to deny these ones because we need to make sure that our table stays aggregated. Otherwise, it's going to get out of control how many routes that we have. So in this case, router 1 as an inbound filter would say something like IP prefix list, whatever the name of it is. So IP prefix list name, permit any address. So we're not going to match any field of the address itself. So 0000/0, but only anything that is less than or equal to 24, LE24. So now as the routes are being received in, the router's not checking the address field itself, it's not checking the network, it's just checking the subnet mask. But saying if it's anything 0 to 24, you're going to allow those in. Otherwise, there would be an implicit deny that says anything 25 to 32, that stuff is going to be denied. If we wanted to do a match, let's say based on just host routes, we would say IP prefix list the name, permit 0000/0. So we're not matching any bits of the address, but the subnet mask is going to be greater than or equal to 32 and less than or equal to 32. Okay, technically, you could just say GE32. So in that case, it's just going to be anything that has a exact host route, so anything /32. So you can get pretty complicated with the logic of the matches that you're doing, but most of the time you're matching just on the exact prefix. So we'll say the subnet 10.0.0.0/24 or 192.168.0.0/16. So you don't need to do any conversion of the mask into decimal. It just shows, or into the to the dotted decimal notation, I should say. It just shows it as the native decimal mask there. How many bits we have for the prefix length. Now, I have a couple write-ups on our blog about this. If you go to blog.ine.com and just search for prefix list, you'll see there's a number of different articles that show different examples of how you would do matches. But the ones that we're going to look at today are going to be fairly straightforward, that are just using the exact route and the exact subnet mask at the same time. Now, like an access list and like a route map, prefix lists do use sequence numbers. So if you want to come back later and delete an individual line or add a new line in, you don't have to delete and recreate the whole entire list. Now, the route map, as we saw with the implementation so far, we need to manually define what the sequence numbers are. So usually you want to do some line numbering that gives you space in between to edit it at a later date. So maybe the first sequence is 10, next is 20, 30, 40. So if you need to come in and insert something between the first two sequences, you could put it as number 15. So it's just like how line numbering works in programming. Prefix lists will automatically just increment the sequence. I want to say it's by 10. We'll look at that on the command line. But the same with access lists. So then when you want to edit it, you can remove an individual line or you can add one back in. So this is going to be used just for doing routing filtering. It's not used for a traffic filter, whereas an access list could be used to deny FTP traffic or to deny web traffic. So this prefix list is just for the purpose of routing. Now the application is either called under a distribute list or under a route map. So for example, in EdgeRP, we could say distribute list, prefix list, its name, in fast Ethernet 0/0. So this would mean anything that is permitted by the list is allowed, inbound. Anything that is denied by the list is going to get dropped. Whereas in the route map, it would depend on the combination of the permit or deny sequence in the route map and the permit or deny logic in the prefix list. Now the second application can get a little bit confusing. This one here, the match IP address prefix list, because you can end up in a double negative. So if in the prefix list you say deny, and in the route map you say deny, it doesn't mean deny, it means don't match. So generally we'll see this on the command line, but when you actually apply this, your prefix list syntax 99% of the time should always say permit. Because you're not really permitting or denying, you're just saying match. Then inside of the route map, that's where you actually say, for this sequence we're going to permit whatever is matched, and then for the next sequence we're going to deny for whatever is matched. But you always want to make sure you don't end up in a double negative. Otherwise it's not always going to have the exact result that you think it does. Okay, the next tool is an access list, which vast majority of time you don't want to use it for routing filters because there are some limitations of it. Access lists generally should be applied as traffic filters, not route filters. Now we'll see this afternoon when we get into IPv6, they fixed the distinction by having an access list being applied as an IPv6 traffic filter, whereas an IPv6 prefix list would be applied to the routing process. But in the original implementations, this stuff overlapped, so that's where it can get a little bit confusing. Now, one of the other problems that you would not want to use the access list for, in this case, is that you cannot match on both the prefix and its length at the same time. So if we had two routes in the table, 1.2.0.0/16 and 1.2.0.0/31, the access list cannot tell them apart, okay, at least from the standard access list. because we're matching just based on the network field. We're not matching on the subnet mask field. So we would be saying check the address 1.2.0.0. That's it. So with prefix list, you can distinguish between the two. Okay, also, it gets a little bit even more complicated when we use extended access lists, because they're different based on the protocol that you use them for. So if we apply an extended access list as a distribute list in RIP and EdgeRP, it means that you want to match where the route is coming from and what the address of the route is. So it's a distribute list gateway filter. You're matching on where did the route come from and what is the particular address. But you're still not matching on the subnet mask. In BGP, there's kind of a weird workaround for this, where it was a stopgap before the prefix list was introduced, where if you take an extended access list and apply it as a distribute list in BGP, normally where the source address field is, it becomes the route, and the destination address field becomes the subnet mask. So for example, if I said access list 100 permit IP host 10.0.0.0 host 255.255.255.0, in BGP that would match the route 10.0.0.0/24. But the syntax is kind of confusing, so there's really no reason not to use the prefix list. A prefix list syntax is generally cleaner when you're trying to do the routing filters. Access list was kind of a hack up until the point where they introduced the prefix list. Okay, another tool we have is the passive interface command. Basically, this is used to disable the routing process on a particular link. So in RIP version 2, if we have a network statement that is matching our fast Ethernet, this means that we're going to send RIP updates out there and we're going to listen for RIP updates on. If we specify this link as a passive interface, it means that we will listen for updates, but we will not send them out. So it's disabling the sending, but it's allowing you to receive. For OSPF and EdgeRP, since the adjacency needs bidirectional hellos, it's going to stop you from being able to form an adjacency on the link. Usually where this feature is used is on a stub network. So it's a host-facing link where you're advertising the network into the process, but you don't want to send hellos out the interface. So let's say on your access layer switches, if you're running layer 2 routing on the access switches, you wouldn't want the VLAN interface itself to be sending OSPF hellos, because you don't want someone to be able to plug their laptop into the network and start hearing OSPF hellos from the network. So you would specify that as a passive interface. But in the case of redistribution and filtering, sometimes passive interface can fix looping problems just by filtering out all advertisements that are going out the interface. Okay, then the last one we have is the administrative route tag. Now, route tagging is used just for our manual purpose to put routes into a different, into general categories that we can match them based on. So this can give us visibility as to what is the redistributing router or what is the source protocol. So for example, in RIP version 2, if I redistribute OSPF into RIP, other RIP routers in the domain, they don't know that this was an external route. There's no field in the routing update that says this is internal versus external. But if I set a manual route tag, as I say, going from OSPF into RIP, set the tag to be 1, I then know in the RIP database anything that is tagged with 1 came from OSPF. Maybe I'll say anything that is tagged with 2 came from EdgeRP. Or anything that is tagged with 100 came from router 1, where anything tagged with 200 came from router 2. So then we would be able to do some route map matching on this and do filtering or possibly change the metric value for the individual routes. So we'll also see that we can use this to prevent route feedback in a couple different designs. So as routes get redistributed from RIP into OSPF, we will set a particular tag value. Say we set tag 1. Then in some other portion of the network, when we redistribute from OSPF back into RIP, we will say if tag 1 exists, then do not redistribute that route back in. So it's going to give us an automatic loop prevention mechanism by setting the tag in one portion of the network, matching it somewhere else, and then making sure that we don't go from RIP to OSPF back to RIP. Okay, any questions up to this point on the different tools that we can use to fix the problem? So either the route maps, prefix list, distribute list, access list, passive interface, or the route tagging.